Okay, so I'm going to tell you about the work we've been doing for the past 6-7 years now with biologists. I worked on many fields in physics and planetology, but that's the first time I worked on biology. And so we developed model, as Niku was saying, to couple planetary modeling, because that we know how to do, ecosystem modeling, because people have been making great progress in modeling ecosystem, try to put the two together to see if we could use that kind of tool to assess habitability and inhabitation in the solar system. So we have the icy moons, you have Mars. I'm going to try to show you example, and of course exoplanet. So I tried to summarize in 1 hour just sketches of results that we have, what works, what doesn't work, and where we can go from that approach that's pretty novel. So here is the Observatoire de la Côte d'Azur. My office is just on the other side, and that's really the view that we have every day. You can testify, because today you are lucky, you have two of us here. We discovered that this morning at coffee break, giving a talk from the observatory. So the general framework of that work is, of course, habitable planets, and you all know about habitable zones. So here you have a sketch with stellar mass on the y-axis and the distance to the star on the x-axis, and each of those dots are exoplanets that have been detected with various detection methods. And in that context, the habitable zone, as you probably know, is you do just simple 1D climate modeling. You vary the composition of your atmosphere between water and CO2, which are two greenhouse gases, and you look at condition and distance to the star, composition of your atmosphere to see if you have temperature at the surface that match a temperature where you will find water in a liquid state. So that's what we define as the habitable zone. You know, that's a concept that's developed in the 60s, quantified starting in the 90s with the work of Kathleen, and then there is evolution with 3D modeling now and GCM modeling that you can do. Just so we are on the same page, what we call habitable planet at the moment is we have all those planets. So here I plotted the flux on the x-axis, and on the y-axis you don't see it, but that's just the stellar temperature that you can relate to the mass of the star. Each of those dots, that's the size of the planet. So you have in yellow the big Jovian planet, and in small blue here you have the terrestrial planet. And what we do is we just superimpose the habitable zone with planets that we are detecting at the moment, and that's what we call habitable planet. That means that it's not a property of those planets, it's just planets that are of interest for further investigation. So where do we stand right now? So habitable planet, people try to say, okay, let's have something that's close to the Earth. So you're trying to look at small objects that have mass and radius similar to the Earth. If you say, okay, I'm going to start looking at planets that are less than 5 Earth mass and radius that are less than 1.5 Earth radius, you have right now 24 planets that are mostly around small stars. You know, that's just the observational bias. So we are able to find those small planets around those small stars. And if you are more generous, and that people vary depending if they want to make a paper out of it or not, you can even say, okay, let's be more generous. We can consider even planet that goes up to 10 times the Earth size and radius that are 2.5 the Earth radius. So you see the mean density starting to go down. That means you have more and more water. So in fact, you have kind of a continuum. What we call habitable planet at the moment is a continuum between Earth-like planets, super Earth, and ocean planet. You know, ocean planet, that's where we have the Asian planet that Niku and his group is working on. So you see all that continuum can be considered as potential target for habitability. Just a few reminder is Earth is here. Right now, we don't have serious candidate of Earth-like planets, or really resembling the Earth around a star resembling the sun. That's what the Plateau mission is trying to decide, and I'll show you later on. The statistic is vary. It goes from not that many, even maybe just a few planets that Plateau will detect, up to about 50, 60. So Plateau mission, very important to constrain here whether or not Earth-like planet around sun-like stars is something pretty common or pretty rare. So that's the status of what we have for habitable planet. And of course, there is one one system that's getting a lot of attention in terms of habitability and trying to see whether or not habitability makes sense. You see it right now, we just put it planet in a zone, then now we need to try to characterize the atmosphere to see if the atmosphere makes sense regarding some greenhouse gases effect to have surface temperature and liquid water. So TRAPPIST-1 system is a prime target for the GWST observation. I was in Baltimore last spring and they were telling me that about 40% of the time of the telescope, and I think it's from the exoplanet, but I'm not too sure, is dedicated to TRAPPIST, to the point that they are thinking about renaming the telescope instead of calling it GWST, just to call it the TRAPPIST telescope. So, but anyhow, the game people are trying to do right now is trying to do with transit spectroscopy atmospheric characterization, try to decide on those TRAPPIST planets that are in the habitable zone, whether they have atmosphere that are consistent with what we describe and what we think are needed for habitability. Here you have a sample spectrum, so you can do big GCM calculation. You have your H2O, CO2 atmosphere. You just vary, you try to optimize, and you vary the surface pressure to see what kind of spectrum you can get, how much transit you need to get. And so you do that to test habitability. So essentially, either finding H2O, but that's not easy because if you just look at the Earth, you know, the upper atmosphere of the Earth is dry. So if you need to, so it's maybe easy to look at CO2. And doing the same thing, people say, okay, if we have the full spectrum, we're not going to look at habitability. So saying if we have proof that there is liquid water on the surface, we can even look at whether or not it's inhabited. And so people start thinking about, okay, it's inhabited, so let's look at methane. There is various ideas in the community. Let's look at methane, let's look at oxygen. Everybody has a good idea. And if you look at the GWST, so you see if you want to start characterizing oxygen, you need to have about 100 transits. So that means you need to use GWST almost for a good fraction of its lifetime. So you're really in a context where a big decision to be made, you know, should we dedicate all the GWST time to keep looking at TRAPPIST, and if they find an atmosphere, to keep trying to see whether or not there is methane and oxygen. And of course, so that's the context of the work. You know, GWST is here. Maybe we have a few objects, and I'm not counting the Asian objects that are important. So maybe we will have a few objects the GWST where habitability is in place. I mentioned to you the Plateau mission, so it's 28. I should update my slide this time I see it. So it's 28 now. Of course, the ELT that's in construction right now is going to look at habitability, and there is already a program in NASA, and the ESA is starting to be involved with the HW mission concept to try to decide what kind of telescope do we really need to build to detect either habitability or inhabitation. And you see that when you look at atmospheric characterization of those objects, necessarily you wonder, okay, what kind of instrument do I need to look at? What should we be looking for in terms of should we have an infrared or large UV telescope? What's relevant for habitability? Should we look at oxygen? Should we look at CH4? Should we look at CO2? So in that context, we decided to start to work because that concept about habitability and biosignature essentially comes from what we know from the Earth's history. You know, that's roughly the three main graphs that summarize the evolution of the Earth over 4 billion years. And when people are thinking about habitability or inhabitation, is mostly they have in mind that evolution that we had on Earth. And you see here, so when people say, okay, let's look at oxygen. Oxygen is, we know on Earth, the 20% of oxygen that we have in the atmosphere come from the invention of photosynthesis, so impact of biology. So people say, okay, if we detect oxygen, then we're going to have a sign of biological activity. Problem with that idea is, if you look at the Earth's history, you know, you had no oxygen for 2 billion years. The great oxidation event is just 1% increase of oxygen in the atmosphere, so that's very hard to detect. And in fact, it's only for the last 600-700 million years that you have enough oxygen in the atmosphere to be able to detect it by atmospheric characterization. So in my viewpoint, oxygen shouldn't be the only thing we looked at when we looked at inhabitation and look at biosignature as oxygen. On top of that, you have false positive. You know, if you have a greenhouse runaway, so if you take the Earth a little closer to the sun, which is going to happen in about 1.2 billion years, then you are going to have all the water steaming into the atmosphere. Photolysis is going to break the molecular water on the upper atmosphere. Hydrogen is going to escape. You should have a big burst of oxygen. So when you look at oxygen, you may have a bigger chance to look at Venus and detect planet getting into a greenhouse runaway than looking for habitable planet. So you have many false positives, and you can keep thinking about that. Methane. So what's the case of methane? That's the constrained methane evolution for the Earth, you know, by geological record. First 2 billion years, probably a lot of methane into the Earth, and I'll show you a calculation that amplified that. Big drop of methane when oxygen appears, because oxygen is a poison. So first massive extension in the Earth's history occurred about at 2.5 billion years ago, because oxygen appeared, all the methanogens died, so decrease of methane into your atmosphere, drop in temperature, Uranian glaciation, and then small methane concentration since then. You know, that's the log scale. So you say, okay, maybe it's useful to look at methane. And CO2, that's a trend that people don't always have in mind, but the CO2, the concentration of CO2 in the Earth's atmosphere has been evolving a lot for 4 billion years. You know, there is geological record that shows that 4 billion years ago, you had about 400 times the CO2 concentration as we had today. And you need to have those 400 times to compensate the faint sun problem. As you know, 4 billion years ago, the sun was 75% its current luminosity. So to have, and we know we have proof that you had liquid water on the surface of the Earth. So you need to have enough CO2 in the atmosphere to have the right greenhouse effect. And that's how you can counter the faint sun problem. The thing is, I'm going to show you that later on, is that we have a global thermostat for the Earth. So as the sun luminosity has increased, the CO2 has decreased in the atmosphere with that trend. So we went for 400 times to where we are today. Okay, so that's another marker. So we can say, okay, if we have a planet that looks like the Earth, maybe we should be looking at CO2. Overall, so what I was saying is you should not only be looking at O2, but also CH4. You need to take all those gases in planetary context. So that means if you have CH4, you need to understand what's the planetary environment. I think there is the what I'm calling the golden target approach is most of us will start to think, well, maybe if I've got one nice shiny planet that has all the right property as the Earth, that's going to be a proof that it's habitable or inhabited. We're taking another viewpoint saying that to have conclusive evidence of whether it's habitable or inhabited, it needs to be a trend on population of planet. I think if we have a large sample of planet and we have repetitive trend like the CO2 evolution, then we have a stronger argument and a strong argument that indeed they may be habitable, they may be resembling the Earth, or they may be inhabited. So in that context, we said, so that's Régis Ferrière, is professor at University of Arizona and also in France, and is a biologist that we start thinking about that problem, saying, okay, can we try to do something better than people have done before? And what people have done before, that's what I was showing you here, is you make your atmospheric calculation, you have your luminosity, and you try to guess, depending on what you have in your atmosphere, whether or not it could be compatible with some biological activity or with some habitability. And what we did is something a little different, is to say, okay, let's do something self-consistent where we take exactly the same thing, except we just put the biology running into those conditions. Then we see how viable it is, and most importantly, because biology always impacts its environment, we get the impact on the environment, the impact on the atmosphere, and then can be a biosignature. So that's the philosophy we adopt. And we start looking at a few test cases. We said, okay, let's try to prove or disprove whether that method is useful in a few cases that gets more and more complex. So that's why I'm calling that the application is the solar system and beyond. solar system, we looked at Enceladus because you have data, so we can do simple modeling. You don't have atmosphere. We looked at early Earth and early Mars because then you have data. Can we couple biology and answer basic questions that were in the community for a long time, like the impact of the methane production in the atmosphere and the impact of chemotroph into the atmosphere. We look at early Mars because we keep saying that Mars was habitable. So we say, okay, we have the biology. Let's run the biology to see whether or not it's viable for Mars 4 billion years ago. And we try to, in a project that Daniela Pai is running from NASA, we're trying to use that to design the future telescope and try to see what could be a good telescope, what should be looking for in terms of exoplanet population and trend. So let me summarize what we found for Enceladus. So we looked at Enceladus because you had the Cassini-Huygens mission that, you remember that mission, you went through around Saturn and you sent a little probe to go around Enceladus. Enceladus is here on your right, that little moon around Saturn that I think is just the space exploration that pinpoint that it was actually very active with jets of water going straight to space. And the Cassini mission, what they did is they had a small probe, and this probe went through the plume and measured the concentration of CO2, H2O, methane. So, yeah, and they get measurement. So you have measurement and you have ratio of those different concentrations. From the planetary modeling, so this is how we understand Enceladus. So here it's on the left, you have a little cartoon sketch. You have that icy shell that we see here, this crackle. So clearly the tidal effect is deforming that planet. Tidal effect is kind of compressing a porous core made of silicate. And so you have a temperature gradient that's rather important. So starting from the ice shell, then you are going to have some ocean in contact with that rather hot or warm enough silicate core. Water circulating, that you have serpentinization, that's what we have on Earth. Serpentinization, that's a reaction between the water and the rocks that produce hydrogen and methane, okay? And what we think is happening, so it's kind of the black smoke that we have on Earth. So then you find yourself in a situation where you have the water recirculating, popping out of the crust. On Enceladus, you see it's very small. It's a small object. You see that's in kilometer. So it's a very small icy ball. Is that you have on those few tens of kilometers, you have jets coming out from here, and we model that just makes the plume outside of Enceladus. Okay? Problem that we had is when you look at that and you make the calculation, is you don't understand the ratio of methane, CO2, and H2 just considering serpentinization. If you look at that, you say, okay, either we don't understand serpentinization or something else is going on. So now I'm digging you into biology. So this is what we did, and that's my view of biology. So that's my perception of life as a physicist. All the work we've done is considering that tree of life, you have two big families. You have the chemotroph, that means bacteria that are just using chemical gradient as energy. They don't need light. And you have phototroph. So all the bacteria that are using light, producing or not oxygen. What we concentrated ourselves, of course, for Enceladus is on that left part. Okay? Enceladus, you have no life appearing, so it's like the bottom of the ocean. So clearly that's the right family we are interested with. And that's where we started to make those calculations. From an evolutionary standpoint, you can also, there is argument in the evolutionary community whether photosynthesis appears first or not. Regarding chemiotrophy, one thing is sure, when you look at those tree of life, you are really looking at stuff that are at the bottom of tree of life. So clearly that's life that was present very early on, and most likely the first signs of biological activity on Earth. And oxygen and photosynthetic oxygen, that's something that came later on, much more efficient, but we are not considering that either. So what we do, just to show you a few equations, is pretty simple. The way it's modeled, it's a box. So it's to model biology as a box with fluxes coming in and out. So you're considering fluxes here. You have this catabolic reaction. So when you're considering some methanogen, you have just H2O consumption and CO2 that's going to produce methane and water. And then what you do is you run those models. So that's population dynamic. So imagine you have several bacteria interacting. So here you have the average cellular biomass. You see you have all your catabolic reaction here. And I think is important is that term. You see this is X, Y, so that's the species. So you have coupled equation for each of those species, methane, CO2, H2. And you see you have a forcing term. So depending on your activity, your biology is going to consume H2O or release, consumes CO2 or H2 and release CH4. So what you do, so here you have sample result of biology. You see all of population dynamic. All that depends on temperature. So it is more or less efficient whether or not you are at hot temperature. If you are too hot, everybody is going to die. You know, that's the breaking point. If you are not hot enough, then it's going to be, you are going to slow down the metabolism, it's going to die out. So that's a simple way of modeling ecosystem. So you have here, we did for Enceladus, we just discovered that, you know, biologists do that all the time. They take bugs and they parameterize how they grow in various conditions and temperatures. So yeah, all that is parameterized. Here, this is the typical bug that we found. We say, okay, an obvious candidate for life on Enceladus is what we have at the bottom of the ocean. And that's run the stuff, told you serpentinization couldn't explain the Cassini result. And here is, so we do that in Bayesian analysis. So what we do is we run the planetary model with serpentinization, all the uncertainties, we fold that in a Bayesian model to say, okay, we are not maybe sure completely about the serpentinization rate, so we make a range of a condition. Same thing for the biology. And so what you have here, you have density, and you have here, I was just looking at the methane escape rate because that was the big anomaly with the Cassini measurement. You see in purple or pink, you have the Cassini data. In blue, that's what you have with serpentinization. If you start to make the biology, you are going to consume CH4, so you are going to change the rate of CH4 produced, so you are going to find yourself here. So that means that's the, no, sorry, when you are, what we are considering abiotic, that's the overall condition where biology can drive. And in green, that's when you have the environment where your biology start to consume the various gases. So you see your density distribution goes to the right into the Cassini data. So what that result shows is if you don't have biological activity, you cannot explain the ratio of concentration of species for the Cassini mission. If you put biology, it does. So we were very careful when we published that work to say we're not claiming we found life on Enceladus, you know. And that was a big debate with the editor of Nature. We said, no, we're not saying we found life. What we do with that model, and I think that's the lesson of those models, is we're trying to put all those ideas on a quantitative basis. So what we do here is we say, okay, we did the best planetary model that we could. We cannot explain the Cassini data. We put biology, bingo, it matched. But I'm a theorist. You give me one data point, I can fit any data point, trust me. So, but on the other hand, where this is useful is you can say, okay, let's think about the next experiment or the next observation that we can do that discriminate between, probably we are missing. So there is two hypotheses. You know, serpentinization, we assume that Enceladus is a silicate core, and maybe because we look at formation model, it's likely that there is much more carbon inside of Enceladus. So the hydrolysis of carbonate and carbonate mixed with silicate, maybe something that we are not accounting. Maybe that's what's going on that explains the CH4 ratio. Or maybe there is biological activity because we don't have only methane. We can start calculating, okay, what are the more complex molecules that can be produced and in which amount and whether or not we can detect them. That's the use from my viewpoint of the method. So now we are talking about people thinking about doing a mission to Enceladus and trying to quantify what kind of detector then we need to get. You know, if we have biomass, what kind of amount of biomass and what kind of detector can we detect it? So that's the question we ask ourselves. Another example, so that was our first case. We say, oh, that looks like it's working pretty well. So we got more ambitious. And we say, okay, let's start to do some real stuff. So let's do a fully coupled planet with, with an atmosphere where we have a photochemical model here in blue, where we do a climate model on top of it. So we have a good idea of concentration of species as a function of altitude in the atmosphere. Then we do a climate, 1D climate modeling. So we have a pretty good idea of the temperature gradient corresponding. Put an ocean, because, and that's where Castine did a paper in 2004 that was a big inspiration to that work, where they were trying to quantify biological activity on primitive Earth. So in orange here, that's the ocean. It's just to keep you awake. So this is the ocean, and that's where we are going to have our biology developing. And to make the thing complete, because I showed you the Earth evolved over 4 billion years, is to use, so to have the interaction between the surface, the ocean, the atmosphere, the ocean, and the inner planet. We use the parameterization of the carbonate silicate cycle, which reproduce that trend in CO2 that I showed you before. So to have the full model that can work for 4 billion years. Okay, so, and in that ocean, of course, we put ecosystem modeling. So we got more ambitious in the planetary model on one hand, and we got more ambitious in the ecosystem model on the other hand. Focusing on the ecosystem model, because as astrophysicists, that's maybe the one you're less familiar with, and maybe not for you, but so what we did, in that case is, here you have your volcanoes, here that's the ocean, here you see you have the burial and the tectonic, so the carbonate silicate cycle is going to bury stuff and send stuff back in as volcanism. And here you have concentration of species into your atmosphere. That's where you need your photochemical model to see the lifetime residence of your various species. They are going to interact with the ocean, so fall into concentration with the ocean. And here you have methanogens, so they just eat. You see, you have the arrows here. It's a bit complicated to read in 2 minutes, but look at the paper. So here it's H2, so we produce CH4. We put acetogen that eats CH4 and can release CH4, and we keep complexify the ecosystem like that. So we did that for primitive Earth. We have a lot of data. One of the big questions that people had and argued about is whether or not methanogenic activity, if that's something that started on the Earth, did that have any impact in terms of biomass produced, and did that have any impact into the atmosphere? So we run our model. So we use a primitive abiotic Earth with those conditions, volcanic outgassing, so you have fluxes, and in that model I showed you before, you have fluxes that goes from volcanoes into your atmosphere and at the bottom of the ocean. Did your climate model, did some photochemistry, carbon cycle, and ecosystem modeling. Okay, so what we found, in fact, is as soon as you put biological activity, immediately you change the state of the Earth. That's something, even with very low efficiency metabolism, like chemiotroph, it's large enough of an impact to change the state of the planet, summarizing what we found. So then you say, okay, so maybe it's important when acetogen started or when methanogen started or the order of the evolution. So we play with different evolution scenarios, and in fact, what we found is what you have here on the right, which is, I think, summarize the result of those studies is here we're just plotting the CO2 CH4 ratio of the atmosphere. Here, that's when you have nothing. As soon as you put biology, you have an impact on the atmosphere. And what's pretty important, so here is as you complexify, you see as you go through that evolutionary path, and you can find different paths, it kind of stabilizes, and it stabilizes very fast in terms of complexity. So you don't need, so that's what first lesson learned from that work is you don't need to have something very sophisticated. As soon as you have 3, 4 species, and you can change the amount of species, the impact on the atmosphere stabilizes in terms of composition. Okay? Second thing that we found, so for me, that's a way of finding a biosignature. You say, okay, if I've got chemiotrophy, activity, and it's not that sensitive to the detail of the biology you are putting into your model, for me, that was very convincing, saying maybe we are onto something, because for me, this is a biosignature. If we are looking for CO-CH4 ratio for planet, if we see that trend, for me, that would be a pretty strong indication that there is some biological activity. And I was not convinced when we started that work. I thought our result and the composition of the atmosphere was going to be very dependent on the time of species we put it in. We went even further. We did thousands of simulations, changing all the biological parameters to see, to put that result on a strong basis. And clearly, that's what we are finding out of it. I was talking to some biologists lately. They say, well, biology is always like that. So that I'm discovering, I'm discovering that. So what we found is, you see, clearly, on short time scale, you change the atmospheric composition, you destabilize the climate. And I was telling you before that when you have oxygen that appears on the Earth, we think the Uranian glaciation comes from the drop of methane. And indeed, if you put something into the system, immediately you change the concentration of CO2 of methane, and you can simulate pretty easily everybody dying out and having glaciation. We did that. We did the first mass extension 2.5 billion years ago that we simulated with our model. And you see, indeed, it responds. And you see, in the 60s, 70s, you had all those stories about the Gaian hypothesis and whether or not life was stabilizing the Earth, and all those Lovelock did a lot of work on that. And what we found, in fact, is, well, it doesn't really matter. Earth is pretty resilient because you can't, on a short time scale, destabilize the system. On a longer time scale, so if you start looking beyond a few million years, and for us it's easy, it's simulation. For us, as we are living global change, that's different, but at least in those simulations, what we see is on longer time scale, it gets mitigated by the carbonate silicate cycle. So immediately, you run your simulation long enough, you are going to find a steady state. And especially in the temperature, you see that we've changed the atmospheric composition. Carbonate silicate cycle, you see in all those cases, you mostly did not change the surface temperature. So biology, carbonate silicate cycle react, and each time you kind of stabilize. Okay, so conclusion of that work, we say, okay, life shaped the Earth, so we could quantify. I think that's the first time we can quantify exactly just simple chemiotrophic life impact the atmosphere. But it did not make it habitable nor habitable like all those Gaian hypotheses that was in the literature in the 60s and 70s. Keep getting more ambitious. We say, okay, it keeps starting to have results. So we say, okay, let's look at primitive Mars. Primitive Mars, because we say, okay, Mars was habitable. And that work started saying, thinking about, okay, if Mars was habitable, if biology started, so maybe there is enough biomass left over that we have sediment and we can dig at the right places to see, to have proof or to try to guide all those rovers that go into Mars. And we found something that got very disturbing. We found that Earth and Mars are two different outcomes in terms of biological activity. I just show you that if you put biological activity on the Earth, in fact, it tends to stabilize it. We've said, it couples with a long-term carbonate silicate cycle. On Earth, on Mars, it drives out Mars of habitability pretty easily. And let me explain you why. So we know that Mars was likely habitable because we have evidence that there is liquid water on the surface of Mars. We are seeing all the geomorphic features that are signs of water. We have aqueous alteration of basalt. We found clays. You have carbonate. So everything points to the fact that there was water, liquid water on the surface of Mars 4 billion years ago. As you know, Mars is interesting because it doesn't have tectonic, And then we think that whatever we found in terms of what happened on Mars 3.8 or 3.8 billion years ago is still there, and we might have trace of what happened on Earth at the same time, but we don't have the record because we have tectonic. So to make Mars habitable is not easy. I told you for the Earth, I told you about the carbonate-silicate cycle and the faint young sun problem. So on Earth, you need to put 400 times the CO2 concentration in the atmosphere to make Earth habitable 4 billion years ago. Mars, 1.5 AU, you need to keep cranking up the CO2. And the problem is you keep cranking up the CO2, it condensates, and then you're losing all your greenhouse effect. So if you're just looking at atmosphere of water and CO2, Mars cannot be habitable 3.8 billion years ago. But we have proof it was habitable. An idea that came out, it's an old idea that came back. It's always like that. It was an old idea and people forgot about it, and he came back to try to solve the problem with Mars. Is in fact, people consider hydrogen and for a long time as a potential greenhouse gases. I think there is papers in the 70s that I found looking at that. Did not really work well. In fact, there is new data. People start looking at cross-section between hydrogen and CO2 at high pressure, and then you see that if you have CO2 and a background of CO2 or H2O that's big enough, so a few bars, then if you start adding up hydrogen into it, then hydrogen is starting to become a greenhouse effect. So you can say, okay, so there's people like Ramirez and group of casting that did that in the little less than 10 years ago. And indeed, we will reproduce all their calculation. You see, this is surface pressure. So you keep increasing your surface pressure. This is the surface temperature. This is your liquid water point you're trying to reach. If you just do CO2, you can keep on cranking and you're far from being liquid. As soon as, so you need to put those new cross-section, those new H2, so three-body cross-section. Then a few percent of hydrogen, suddenly, once you reach a few percent of hydrogen, then you start to have Mars habitable. And say, okay, maybe we have the solution to get Mars habitable from a climate modeling standpoint. So we did that. Okay, so let's try to do to put some biology into it. So we did some biology a little different than from the Earth, where we had ocean. We say on Mars, maybe there was some liquid water, but let's be more realistic. Probably it was some water, but with biology getting into those porous regolith, which are pretty, which resemble, it's not water, it's more saline brines. And biologists have data on those species that live in saline brines. So that's the model that we put it in place. So it's just an atmosphere, and inside of Mars, possibility of biology to live in the porous regolith, okay? And with your climate model, then that expand habitability because you can be here and you have a temperature gradient, so you can still have biology evolving inside your crust. And then, as I say, so what happened? Okay, let me show you what happened. As soon as you put the biology, remember that's the hydrogen that makes the planet habitable. If you put methanogens running into it, they're going to eat up the hydrogen, and it goes pretty fast. So in a few million years, you eat up all the hydrogen, and then you lose your greenhouse gases. So we have 1D calculation. We did a 3D projection of those 1D calculation to get the surfaces of Mars and different spots where it could last longer.
What is the color scale?
Sorry?
What is the color scale?
It's just ice coming in. So white is, so because if you have your hydrogen, you are going to have surface temperature where you don't have ice. And if you're starting eating up the hydrogen, then you are going to condensate and make some ice on top of it. So that's ice, or, it's not ice, it's, sorry, I shouldn't say ice, it's just inhabitable. It's just killing the interface between the crust and the atmosphere, okay? So that's, the color is more like that. It's probability of having activity. So white is you don't have any biological activity, and sorry, it's not ice. White is you don't have any biological activity. Red is you have biological activity, okay? So what we found is Mars is habitable for methanogens. So we can have ecosystem running. But as soon as you heat the hydrogen, then the surface temperature decreases because you don't have atmosphere into your, you don't have enough hydrogen to be above liquid water or to be above, to freeze your brine, and then you run out of habitability. And you can play because there is some uncertainty. You know, what's the freezing point of brine of different concentration? So that's something pretty open. So you can play with different kind of salt concentration into your brine. And you see that either case, either it's high melting temperature or low melting temperature, you know, you cannot find a way to not heat up the hydrogen into your atmosphere. Oh, I did it here. So you see, so second result. So you see the impact of biology in that case. It makes a lot of sense because you heat up the hydrogen, so Mars becomes inhabitable, so you kill the planet. We got a lot of media attention with that result. That was not the point of the paper. We were just trying to find, you see, those kind of map to see where the biomass could be produced. Okay, so that was the point, saying, okay, if that lasts for a while, then we have some sites that keep the right temperature for longer so that you have more biomass production, and then that's where we should dig. Okay, so let me finish, I still have a few minutes. Let me finish for the last application we did of the model is to look at habitable planet. And this time we put it biology, but I'm going to concentrate on trying to validate habitability. So I come back to my graph that I showed you before. Is if you look at the Earth's evolution of PCO2 over time, you see you have a drop of concentration of CO2. Drop of concentration of CO2 is because you have the carbonate silicate cycle, and carbonate silicate cycle need to have water to be going. So that could be a sign that indeed you have water, liquid water on the surface, because that gets into the carbonate silicate cycle, and then it could be an indirect way to prove that concept of habitability, which is just right now just theoretical prediction. And the idea here is we say, okay, if we have a trend of exoplanets, so if we have 20, 30, or 40 exoplanets, and out of those 40 exoplanets, if you have 15 that have those kind of trend, you are going to be pretty convinced that maybe something similar to what's going on the Earth is happening. So let's see if it's true. And that's an idea that don't come from us. Is an idea that comes from Lemmer and Kathleen group. So Kathleen looked into that in the 2000. So we're in competition, you know, a little bit with Dave, but it's fair competition. So what they did is they take their carbonate silicate cycle. They vary all the parameters. The parameterization is rather complicated because you are parameterizing, you know, the weathering of the continent. You know, you have all kind of parameters, and it's always you reproduce the Earth's history, but you say, okay, there is no reason that the northern planet is going to be as similar. So you vary all those parameters, and that's what they did. And they say, okay, we have samples of planets that have a carbonate silicate cycle where they take the most parameter that you could vary, and we did the same, and you find those kind of trend. Okay, so you have those plot here. That's the PCO2 concentration. And that you see for the Earth, I was looking at that as a function of time. For exoplanet, because we have a snapshot at a given time, of course, we are going to look into incident flux. So depending on the flux, you know, and indeed you find you have a log linear relationship between PCO2 and the flux of the star if you do have a carbonate silicate cycle. And even if you vary it by, you know, large amounts, so more or less land coverage, more or less ocean depth, so you can play with all those parameters. But if you have, for a set of planets that resemble the Earth, that carbonate silicate cycle working, you do have a trend. You see, that's what you have a trend in terms of PCO2, concentration of CO2 in terms of incident flux. And they say, okay, how many planets do we need to statistically, Bayesian analysis, you know, to distinguish that trend? And they say, okay, you need to have 85 planets that do have that to start distinguishing that trend over uniform background. So clearly, you know, even if we are thinking about HWO, the next instrument clearly is way far out of reach. We are not even sure there is 85 Earth-like planet surrounding us that we can characterize characterize their atmosphere. So we looked at that and said, okay, maybe we can do something slightly different. So you see, we have all our model that I showed you, and I'm not going to, so that's the Earth model, and we can vary all those parameters for 4 billion years and do exactly the same calculation that we did. But we did it slightly differently. We said, okay, why should we be looking at planets that have a carbonate silicate cycle that's tied to tectonics? If we looked at the solar system, that's not the situation. We know that in the solar system, we have kind of two dominant regimes, and Earth probably has oscillated between the two. You have the stagnant lead regime, like Mars and the Moon, and the early time, the first billion years on the Earth. Likely Venus. Venus has an episodic regime where from time to time it kind of bursts and recycles completely its surface. But you can say, okay, you have one dominant regime is a stagnant lead, so you just have your planet cooling down, having some volcanoes and no tectonic. And you have the mobile light regime that what we have on Earth for at least 3 billion years. And you say, instead of saying, okay, we are going to try to discriminate between a mobile light regime against a background, we are going to say, can we discriminate between a stagnant lead and a mobile lead background? And essentially, you know, if you look at those carbonate silicate cycle, in the stagnant lead, you don't have continental weathering because you don't have a new basalt coming into the surface, so you don't have continental weathering. You still have seafloor weathering, so you have the ocean, and at the bottom of the ocean, you have your seafloor weathering, and you are going to have, so that's parameterized. People have looked into that, and you can characterize what kind of volcanic activity you are going to get. So you can have, as a function of time, you know, depending on the size of the planet, for 1-2 billion years, you are going to have bursts of CO2 and hydrogen into your atmosphere. And we compare that to the mobile light regime, where indeed you have continental weathering because you have the continent rolling over, then you have fresh basalt coming into play, and then you can have continuous weathering. You have seafloor weathering, and that's parameterized. We know the Earth's volcanic outgassing rate. And of course, I'm mentioning the Venus case, but that's not, Venus is in between. So, so we run thousands of simulations. So those graphs are a little bit not easy to read, but on the left, you have the mobile lead, so what you have on Earth, and on the right, you have the stagnant lead regime. And each of those points, you know, that's, you know, we do simulation, calculate the steady state between the atmosphere and the carbonate cycle, and finding steady state condition for different time, because, you know, you have outgassing that depends on time and the various parameters of the carbonate silicate cycle. And this is the scale that's useful to read that graph. This is a function of planetary age. So if you are blue, you have young planet, less than 2 billion years. If you have yellow, you have older planet. And in fact, what we are finding is what you can imagine is you know, terrestrial planets, they start to have volcanism, and they can put CO2 and methane into the atmosphere for 1-2 billion years, because that's enough. And that if you are at the right position for that time, that's enough to keep it habitable. That's your finding on the right side here. That's probably what Earth did the first billion years. But as soon as you go beyond 2 billion years and you don't have that feedback loop for CO2 to control the amount of CO2 as your luminosity is increasing, then you start here and you don't have any habitability. And on the right, on the left, of course, you know, if you have your carbonate cycle, you find that log linear relationship. We did exactly the same thing that Kathleen. We moved all the parameters, so we tried to do something pretty simple. But now, once you start playing with Bayesian analysis, you can say, okay, can I discriminate between the two regimes, and how many planets do I need to do that? And if you're starting to say, okay, I'm going to discriminate between the stagnant lead and the mobile lead regime, which are two dominant regimes that we are finding in the solar system, and you can start getting out with 25, 30 planets with different, you know, so that's the Bayesian factor, so with different confidence rate. But that gives you an idea that maybe, you know, if HWO, you say, okay, maybe they want to go in the 25, 30 ballpark range, maybe that could be enough to give some indication. And that's the goal of those calculations, is to try to say, okay, does that make sense to start to be looking at the concentration of CO2 to quantify habitability, knowing the capability of the instrument that we have and that we will have for the next, at least for my lifetime, for the next 15 years, right? So that's the part of the work, so trying to prepare, so that's the work we do with Daniela Pai, trying to prepare those future space observatory and their requirement, and with some hypotheses that would make sense to be tested. So I'm kind of running out, but so that's, you can predict, you know, how many planets that you can detect with direct imaging and stuff, how many atmospheric characterization you can do, playing with those numbers that I was telling you about at the beginning of the talk regarding what we consider an habitable planet in terms of size, in terms so you can be more or less restrictive, in terms of planet that you can detect. You see here we got pretty generous. We looked at planets that have radius less than 2 Earth radius. So it's pretty big and it's pretty different from the Earth, but that's a start. You can refine that. Look at that for G and K type stars, because that's something we want to look at. And what we found is something that's what we are writing at the moment. What you find, in fact, is we're not that good at predicting how many planets, Earth-like planet around G and K type star we are going to get. We don't know if it's, you see I was just missing one, but that's the one we use for the calculation. But you see the spread of planet right now, you know, it goes from, there is maybe 6 Earth planets, if you believe Christophe, there is maybe 0.7 Earth planet that we are going to find with Plato. Maybe there is 24, if you get more generous, you are here, and we are here about 15, so we are in between. So Plato mission at least going to characterize and restrict that number in terms of how many planets do we have. Then we said, okay, if we have 25, maybe that's enough, or maybe at least we know if it's one way to try to quantify habitability. All right, so I'm leaving you that summary. I'm roughly on time. I'm on time, right? We started a little late. So summary, so I'm trying to show you that so the goal of all that work is to try to look at habitable planet and inhabitability, trying to put biosignature into a quantitative basis. You know, for exoplanet, I showed you the question of habitability, but we have exactly all the data for how much methane do we get into the atmosphere when we put biological activity, what kind of instrument and sensitivity is required. So I think it's an interesting approach. We have some funny first application where it seems to work, and what we are working on right now, so on the biological side, is to include photosynthesis, because all the work we've done is just chemiotrophy. So we are developing to add up photosynthesis, which has even a bigger impact on the atmosphere. And we are better coupling of the interior, and we're focusing right now, because there is a mission to Jupiter's moon, so of course on Europa, and on working with Niku on Asian planets. Thank you.